Welcome to Unit 2, Lesson 2, Solving Cubic and Quartic Equations. So we've looked now a lot at solving quadratic equations, and so the next step is to try and use similar skills to solve more and more complex polynomials. And the next most complex ones are cubic and quartic. So let's first just take a quick moment to think about what that means. So that word cubic, what makes something a cubic equation is if we see the highest exponent on a variable as a 3. And that's where that word cubic comes from, is that somewhere along the way you'll see a cubed variable or like an x cubed or a y cubed or something like that along the way. And that's what makes an equation like that cubic. Specifically, again, when the largest exponent that we see on a variable is a 3. And we also sometimes use the word degree, to represent the highest exponent that we see. So for example, quadratics, we say are degree 2 because they have a squared. And linear equations are just degree 1 because they just have an exponent of 1. So cubic equations, we say, are degree 3. And quartic is just the next step in that. It's when the largest exponent you see on a variable is a 4. So you might see an x to the power of 4, and we say that those are degree 4 equations that come from degree 4 polynomials. So I use that word degree, and I wanted to make sure we review it a little bit, because it's going to allow us to have an idea of what we're looking for when we try and solve each of these. Because there's a really important fact that we need to make note of first. A polynomial of the nth degree has n roots. So whatever degree it has, that's also how many possible roots we can find. Which is why when you were first learning how to solve equations, you were just solving linear equations or degree 1 equations. They only had one exact solution that you could find. But then last year, when you moved on to quadratic equations, those were degree 2, and you notice that there are often 2 different solutions that you could find, or sometimes it ended up being 2 of the same number popping up, but it would always break up into 2 different factors or 2 different pieces from the quadratic formula. So 2 solutions pop out of a degree 2 polynomial. Well, that means we can imagine that if we're doing a cubic or degree 3, we should have 3 different solutions potentially. And a degree 4 or a quartic equation will have 4 roots that we're looking for. The other thing that's taking us a step further from last year is, just like in our previous lesson, we're not just looking for real numbers, we're actually going to extend it so that the x values we want are any numbers that are potentially complex. So maybe even things that use imaginary components as well. Now to do this, we're actually not really going to learn any brand new skills. We're just going to review and reuse a lot of the more complex factoring skills that we learned in our last unit. So let's see an example. So here you see that the highest exponent we have is a 3. This is a cubic polynomial expression that we have on the left side, which means overall we have a cubic equation. And that means we're looking for 3 roots. So what can we do with this? Well, if you look carefully at what we have on the left side, we can try and factor it. Now, when we look at the different things that we have here, we can't just think of it like a regular trinomial, and we can't do difference of squares or anything like that, but you might notice that we have some common factoring we can do. So, oops, shouldn't start with the equal sign there, my mistake. We can definitely factor out a 2 from every term, and since the first term is negative, I'm actually going to try and make my next step simpler by factoring out negative 2, and they all also have at least one factor of x. So what's that leave me with? Well, it leaves me with positive 2x squared plus 9x minus 5 inside of a bracket beside that, and that's still being equal to 0. Now, notice that, again, everything is on one side and 0 is on the other. So part of the skill that we're using here is the same skill that we've used in previous lessons. We're just trying to break this up into as many separate factors as we can, and then each separate factor could possibly be equal to 0, and that will lead us to separate solutions. So right now, we've actually already found one of the factors. Even though it's not in a bracket right now, this little piece here that we've just common factored out, negative 2x, that's going to be one of our different solutions. Where else can we go from there? Well, let's break this up and say, well, if this was equal to 0, then the whole thing would be 0. So that means if x itself is equal to 0, then this whole thing becomes 0. But what else could be true? It's either that's the case, or this piece that we have in brackets, 2x squared plus 9x minus 5, that could be equal to 0 as well. But now what we recognize is that the thing that I just wrote down there on the right side is really just a tricky trinomial that can be factored using our tricky trinomial skills. So if you take a minute and do that, I got 2x minus 1 and x plus 5, and that's still equal to 0. And so that itself now breaks up into two separate roots. And you can do a whole little calculation if you want. I'm just going to sort of skip ahead to how this would break up. So this one produces an x value of positive 1/2 when we rearrange it after setting it equal to 0. And this one produces an x value of negative 5 when we set it equal to 0 and rearrange. So what does that mean? Which one is our solution? Well, all of them are. Just like we thought, we started with a cubic polynomial, which is degree 3, and we found 3 separate roots. So we can make a final statement and say, therefore, the solutions are x equals negative 5, x equals 0, and x equals 1/2. So for my next examples, I'm not always going to write out the full sentence like this to summarize it. I might just put a box around each of my solutions, but that's the idea, is that all 3 of these are truly different solutions, meaning all 3 of those values will make the left side equal to right side. And again, notice that we did that the exact same way overall that we've solved by factoring in the past. It just means that the factoring we had to do was a little bit more complex and took 2 steps. We had to common factor and then do trinomial factoring. This one now is a quartic polynomial, and that's because it's got a x to the power of 4 in it, which means we're actually going to be looking for 4 separate roots potentially. Now this one, though, we know, even though it's actually a quartic equation, it looks a lot like a simple trinomial in a quadratic as well. So we can sort of tackle it in a similar way. We have factored this in previous lessons. So we essentially factor it the same way that we would have if it was x squared minus 24x minus 25. It's just that instead of each of our factored brackets starting with an x, they're each actually going to start with an x squared. But the other pieces in each bracket that make it work would be minus 25 and positive 1. So I've just factored that again using skills from our previous unit. And I warned you last unit that those factoring skills would be very important for us. That's still equal to 0. So what does that mean? It means we can break this up now. Either x squared minus 25 equals 0, or x squared plus 1 equals 0. Let's tackle each of those situations. Now, for x squared minus 25, you could actually factor that because it is a difference of squares, but there's an even simpler way to do it if you just rearrange and take a square root. So x squared, for example, is equal to positive 25 if I move that to the other side. And remember, if I'm square rooting both sides, it's not just the square root of 25, it's the positive or the negative square root. So my answer there could be positive or negative 5. So again, what I've already found is 2 out of my 4 solutions just from that one calculation in the one factor. What about the other factor? So x squared plus 1 equals 0. Let's try and solve it the same way. That would mean x squared is equal to negative 1. And then if I want to find x, it means I have to take either the plus or the minus square root of negative 1. Well, up until last year, you would have had no idea how to deal with this, but now we know how to deal with this. We can say that this is really x could be plus or minus the symbol I. So each of those, whether it's positive 5 or negative 5, or positive I or negative I, those are all perfectly valid solutions. So those are two of them, those are the other two, and we have found all four of our solutions in this case. Let's try another one. I'll just get rid of some of this just to make it a little bit neater for me. So now this once again is a cubic that we're dealing with. And we know it's cubic because we see a power of 3. That means we're looking ideally for 3 roots. This one though doesn't have any simple common factoring that we can do. So if it doesn't common factor, and we know it's not a trinomial and we can't just do a difference of squares or anything like that, really the only other tool that we have available to us for something like this is grouping. So let's try and group things together. I'm going to group these two terms together and think about any common factors I can pull from them. And I'll group these two terms together and think about common factors I can pull from them. So from the first two, they definitely each have at least 2 powers of x. So I'm going to pull an x squared out from them, which leaves 3x, and then just a 1, plus 1. From the other chunk, the other orange piece that I blocked off there, I can factor out positive 8. And that leaves me with, once again, 3x, hey, plus 1. And that's all still equal to 0. And now I recognize that each of my large chunks have a common piece to them. They each have this bracket in common. So 3x plus 1 suddenly becomes a common factor that I have on my left side overall. So just like I do with any other type of common factoring, I pull my common factor out in front of everything, and I create a new bracket beside it with what's left over when that's divided away. So the first chunk has an x squared left over, the second chunk has a positive 8 left over, and that's still all equal to 0. So now I started with something that was just a fully expanded out cubic, and now I've actually broken it down into separate factors where one is a linear factor and the other one's a quadratic factor. So from there, let's break those down and solve them separately. This, again, is the overall purpose of these factoring skills, is that when we can break it up into separate factors, each factor has a smaller degree and is therefore easier to solve. So it's either a simple linear, like we're dealing with in this one here first, or it's going to be a fairly simple quadratic, like we'll deal with in our next bracket. For this first linear one, we'd say 3x plus 1 could equal 0. So if we do a little bit of rearranging, that means x would have to be negative 1/3 to make that equal to 0. So that's one of our possible solutions. But we also know or x squared plus 8 could be equal to 0. And let's start rearranging. That means x squared would be equal to negative 8, or x is equal to plus or minus the square root of negative 8. And if you remember, the square root of 8 can reduce to 2 root 2. So that means the square root of negative 8 is going to be 2i root 2. So it's going to be plus or minus 2i root 2. So the 2 root 2 part comes from simplifying root 8. That's from previous lessons. And then the I comes from the fact that it was actually a negative 8 underneath that square root. So again, that's 3 separate answers that we found. So our 3 solutions are x equals negative 1/3, x equals positive 2i root 2, and x equals negative 2i root 2. So even though I really only circled, or I guess put boxes around 2 different things, keep in mind that this second one here is actually representing 2 different solutions because one's positive and one's negative. So overall, we have found 3 solutions or 3 roots, as we expected. Let's take a look at this one now. And it looks like a much more complex polynomial than some of the ones we've dealt with so far. And just by looking at it, it might not even be obvious whether or not this is cubic or quartic or what we're dealing with exactly here. But probably right away, you're going to recognize that regular trinomial factoring that we do is not going to work. It's not difference of squares. There's no real common factoring we can do, and this doesn't even factor well by grouping. The only other trick we have then is to look for any possible substitutions that we might be able to make. And substitution was another trick that we've learned in previous lessons, and it can be really useful when we see something that looks a little bit complex that's inside of a bracket but repeats itself in multiple places. So for example, that would be something like this: x squared minus 5x, which we see that whole bracket being squared, but then we see that entire same bracket appearing later on as well. So when you see situations like that and no other types of factoring work, substitution might be a really useful trick to try. So what I'm going to do is I'm going to create a brand new variable. Doesn't matter what letter you give it, but I'm going to call it y. And I'm going to let y represent x squared minus 5x. So that for now, at least, for the first couple steps that I do, I can think about trying to factor this just based on y, and then substitute back in to replace y with what it originally was equal to. So I'll show you what I mean by that as a little review. This is now going to become y squared minus 2y minus 24 equaling 0. And as soon as we see this, we recognize that this is just a simple trinomial. Could factor into y minus 6 and y plus 4. And that's going to be equal to 0. From here then, that breaks up into two scenarios. Either y minus 6 is equal to 0, or y, oopsie, write that a little neater, y plus 4 could be equal to 0. But again, in the end, I don't want y to be involved at all. It was just sort of a new thing that I introduced as a little trick to help me out, but in the end, I really am concerned with x and different values for x. So before we just solve and try and figure out what y is, really we're still trying to figure out what x is. So now that we've used y to help us do a little bit of factoring earlier on, let's substitute back in place of y. So I'm going to take y and sub it back out and replace it with x squared minus 5x. But remember, I still have a minus 6 equals 0 from that equation. And over on the other side, similar idea, x squared minus 5x, but now it's plus 4 equaling 0. And again, the idea is that I just replaced y now with what y originally was meant to represent, which is x squared minus 5x, and I did that in both cases. But now, if you look carefully at these two basic scenarios that it's broken into, each of them is actually going to produce two separate solutions. And we know that because now we have two separate quadratics. And we know that quadratics produce two solutions because they're degree 2. So overall, we're going to end up with 2 on the left side and 2 on the right side. We're going to end up with 4 separate solutions, which means really this thing was a quartic all along. It was a degree 4 polynomial equation. So if we factor on this left branch, it could be x minus 6 and x plus 1 equaling 0. If we factor in the other branch, it would be something like x minus 4 and x minus 1 would work. And that's going to be equal to 0. And then I can use that to make one grand overall statement and say each of these factors, whether it's x minus 6 or x plus 1 or x minus 4 or x minus 1, each of those factors is going to produce one solution. So I can say, therefore, x could be equal to, based on those, x could be equal to 6, or x could be equal to -1, or x could be equal to +4, or x could be equal to +1. So all 4 of those are possible solutions that would make the left side equal the right side in this case. So again, don't be afraid to use that substitution strategy if you ever feel that any of the other strategies aren't working for you, and if you particularly see a pattern emerging like we did with this x squared minus 5x bracket that was appearing more than once. Let's try one final type of situation that's actually going to again, boil down to a quartic situation, but you wouldn't really recognize that at first when you look at it. So if you see a very strange expression like this, again, don't concern yourself or worry too much right away about whether or not it's cubic or quartic or exactly how many roots you're looking for. Let's just try and solve it as best we can. Now, again, it looks very confusing and very complex, but if we look carefully, we recognize something that substitution might help us with, because this weird thing inside the bracket, x plus 1 over x, actually appears identically in this other bracket here, x plus 1 over x. Let's try making a substitution there. And let's say I'm going to let the variable, well, it doesn't matter what letter, but let's try a different one this time. Let's let a equal x plus 1 over x. Because I think we can agree that x plus 1 over x is a tricky little expression to work with, but the letter a is much simpler to work with. So let's see what happens there. Suddenly this becomes a squared minus 7a plus 12 equaling 0. That factors pretty simply because it is a simple trinomial. A minus 4 and a minus 3 are the two factors. And that's still equal to 0. So that breaks us up into two scenarios. Either a minus 4 is equal to 0, or a minus 3 is equal to 0. But at this stage, just like we did in the previous one, now that we've used a for what we wanted to do, which was to factor that original very complex looking polynomial, now we can substitute the a back out. So a is going to be now replaced with x plus 1 over x. But I still have a minus 4 equaling 0 from that first branch. And in my other branch, it's going to be x plus 1 over x, but I still have a minus 3. And the whole thing's still equal to 0. Now, I've got to try and solve all of this now. And it looks like I've just made things much more complicated for myself. But it is still an equation. And so because I've got a denominator here, I've got x in a denominator, it looks like it's very tricky to work with. But because this is an equation, I can do a special trick to get rid of anything that's in a denominator. So I can multiply everything on one side by anything I want, as long as I multiply the other side by the same thing. So essentially what I'm going to do is take each of these equations and multiply them by x. I just put a dot x because I didn't want to put a times symbol, because then you'd think I was putting two x's or something, but that's the idea, is I'm taking all of this as well, and I'm going to multiply by x. And I can do that again as long as I do the same to both sides. And it's really easy to do that to the right side of each of these, because 0 times x will still be 0. So I'll still have an equation that's equal to 0 on the other side. But when I do that, I get x squared plus 1 minus 4x equaling 0. Or if I rearrange that a little bit, x squared minus 4x plus 1 in the regular standard form of a quadratic. I get a very similar thing happening in the other branch. And I'll even just jump ahead to the slightly rearranged version. I would get x squared, and then I'll put the minus 3x next, and then I have a plus 1 at the end. And that's all equal to 0. Well, in both cases, these actually, even though they look fairly simple, they do not factor nicely. And there's really no other factoring strategies we have for these, but as long as we've broken them down to quadratics, we don't have to be able to factor them or solve them any further. We can just use our quadratic formula to help us out. So in this case, we would say a is equal to 1, b is going to be negative 4, and c is going to be equal to positive 1 as well. A is equal to 1, b is equal to negative 3, and c is equal to positive 1 for this one as well. Substitute into quadratic formula. You can pause it here if you want and try this for yourself. But remember, we're not trying to just find some approximate decimal answer on our calculators. We're trying to work out what the exact value would be, which might still include some radicals if they can't be reduced any further. So it would be like negative of negative 4 plus or minus square root of -4 squared minus 4 times 1 times another 1 all over 2 times 1. Or in other words, it's like positive 4 plus or minus square root of 12 all over 2. Can make that a little bit simpler by saying it's 4 plus or minus, now 12 can be written as 2 root 3, and that's all over 2. And then I just reduce by dividing everything on top and everything on the bottom by 2. So really, I can say x is equal to 2 plus or minus root 3. Now remember, that's not just one solution. I've actually found 2 solutions, because that means, and I'll maybe just write this separately, therefore, that could mean x equals 2 plus root 3, or x equals 2 minus root 3. Both of those solutions are valid. Now we just need to do essentially the same thing, but with the other branch. So negative of -3 plus or minus the square root of -3 squared minus 4 times 1 times another 1 all over 2 times 1. So it's equal to 3 plus or minus the square root of 5 all over 2, which can't be reduced or really changed any further than that. So that means we can say, therefore, the other 2 solutions are x equals 3 plus root 5 over 2, or x equals 3 minus root 5 over 2. And those would both, again, be perfectly valid solutions. And I know that seems weird. I know you're very tempted to say that's not the solution because we haven't finished solving it yet. We have to take all these pieces and subtract them and divide them. How can we have an answer that has all these different pieces, like 3 plus root 5 over 2? At first, your brains are going to be really bothered by that. And you'll say, we need to keep solving it. We need to find the exact answer. But we have. We have found the exact answer. There is no other way to write down those exact solutions. The only other thing we could do with these calculations is to punch them into a calculator and then approximate it by just rounding off whatever decimal number comes up. But the decimal number that these answers produce will have to be rounded off eventually. There is no other way to write their exact value than the way that we have written these down. So when we look for exact solutions, we need to possibly include radical pieces as part of those solutions, and that's okay. That's actually better in the long run than just rounding off some of our answer that we don't feel is needed, because all of this solution may still be needed in future calculations. Take some time and make sure you practice as many of these as you can, but as you're seeing, it's really still using a lot of those same factoring skills that we spent a lot of time reviewing in our previous unit.